In this video lecture, we will address the topic simple linear regression. Linear regression is a statistical method for quantifying the linear relationship between two or more variables. The method is very common and has an important application in quantitative research areas such as epidemiology, biology, and econometrics. In this lecture, we will focus on simple linear regression. A simple linear regression consists of only two variables, one response variable and one explanatory variable. The response variable usually represents an outcome such as an illness, condition, or quality of life. The explanatory variable represents a factor that affects the disease, condition, or quality of life. The response variable and explanatory variable are usually denoted by the letters y and x. In the linear regression, the response variable y should always be numeric, while the explanatory variable x can be categorical or numerical. In this lecture, we will focus on the relationship where both the explanatory variable x and the response variable y are numeric. The response variable and the explanatory variable are also referred to as dependent and independent variables. This is because the response variable depends on the explanatory variable and because the explanatory variable comes before the response variable in time. For example, when assessing the effects of maternal smoking during pregnancy on infant birth weight, smoking would be the independent variable and birth weight the dependent variable. If the response variable y depends on several explanatory variables at the same time, this is referred to as multiple regression. We will not address this issue in the current lecture. Before we start illustrating an example of simple linear regression, we will take a closer look at what we mean by a linear relationship. Suppose we have a coordinate system with two numeric quantities, x and y. We let y be the dependent variable and thus on the vertical axis, while x the independent variable and thus on the horizontal axis. We say that the relationship between x and y is linear if the relationship between the numerical values x and y is a straight line. In other words, we have a linear relationship between two variables if we in a two-dimensional coordinate system have a straight line without curves. A linear relationship between x and y can be written as a mathematical function. Y equals a plus b times x. As previously defined, y is a dependent variable while x is the independent variable. Also, we have two other sizes, a and b. The quantity a is called the intercept or constant term. The intercept is the point where the line intersects the y-axis, or in other words, the value of y when x equals 0. The quantity b is called the slope. The slope tells you how much a straight line rises or falls. In other words, the slope quantifies the linear relationship between x and y. If x increases by 1 unit, for example when x increases from 1 to 2, then the slope tells you how much the y value increases or decreases. To sum up, it is the values of a and b that determine what the straight line looks like. Now, in the current figure, the intercept is 2 and the slope b is 3. In this case, y increases by 3 units when x increases by 1 unit. Note that no matter where you are on the x-axis, y will always increase by 3 units when x increases by 1 unit. When the slope b is positive, as in this example, we say that the relationship between x and y is positive. When the slope b is negative, we say that the relationship between x and y is inverse. In an inverse relationship, y will decrease with the increasing values for x. When the slope b is 0, we have no change in y when x changes. There is no relationship between the variables x and y. In a survey, pairs of observations of x and y will usually not lie on a straight line. They will be scattered throughout the coordinate system like a point cloud. The points in the diagram here show pairs of observations for the number of cats in the home and health-related quality of life for 9 persons. Note that we let quality of life be the dependent variable and thus on the vertical x-axis, and let the number of cats in the home be the independent variable and thus on the horizontal axis. In this example, higher quality of life scores mean a better quality of life. Based on this scatter plot, it appears that people with fewer cats in the home have a lower quality of life than those with many cats in the home. For example, one person with 0 cats in the home scores 1 on the quality of life scale, while a person with 6 cats in the home scores 11 on the quality of life scale. We will now take a closer analysis of whether there is a statistical relationship between the number of cats in the home and health-related quality of life. In other words, we want to investigate whether quality of life depends on how many cats one has in the home. To answer this question, we can fit a straight line through the point cloud. In other words, we want to draw the best straight line that shows the trend of the points in the diagram. However, the line cannot be fitted by the naked eye. There is only one solution for this line for these points. The solution is found by doing a regression. We start by writing down the mathematical expression for an arbitrary straight line in our example. Since health-related quality of life is the dependent variable, we replace y with the quality of life. Likewise, we replace x with the number of cats in the home. Remember that the quantities of a and b determine what the straight line looks like. The goal of regression is therefore to estimate the correct quantities of a and b in our example. We call these quantities regression coefficients. One way to illustrate regression is as follows. Suppose we draw an arbitrary straight line in our diagram, which does not necessarily need to be well fitted. But if we continue to draw new lines and keep going on until the vertical distances from each point to the line is minimized, then we have found the right quantities of a and b that give a best fitted line, shown here as the orange line. There are several methods for finding the correct regression coefficients for our line. One commonly used method is called the least squares method. It involves finding a and b that minimize the sum of squared distances between each observation point and the regression line in our diagram. We usually leave a statistical software package to find the right regression coefficients for us. In this example, the regression coefficients A was estimated to be 4.8 and B was estimated to be 0.6. We can now use this line to answer the question of whether health and related quality of life depends on how many cats you have in the home. It seems that we have a positive relationship between the number of cats in the home and quality of life. For every unit cat increase on the x-axis, the quality of life score on the y-axis increases by 0.6. Using this line, we can also predict the average quality of life scores for a given person. For example, the quality of life score for a person with no cats in the home is 4.8 on average. The quality of life for a person with 5 cats in the home is 7.8 on average. Be careful with prediction outside the data range of the X variable. Suppose in this example we have used a quality of life instrument that goes from 1 to 15. If we wanted to predict the quality of life for a person with 20 cats in the home, the score would add up to 16.8 when using the regression model. However, this number is higher than what we can measure from the instrument. In other words, the prediction outside the data range here would be invalid. An important condition for performing linear regression is that the underlying relationship between x and y is linear. If the relation is not linear and we still use linear regression to quantify the relationship, we may obtain the wrong results. The example here shows a U-shaped relationship between x and y. In this case, it would be wrong to use linear regression. Before conducting regression analysis, it is therefore always important to examine that the relationship is approximately linear. This can be done using a scatter plot, as we did in the cat example.